Unit 4, Access Control, Part 1. Note that this topic is not in the same order as the equivalent topics in the Sean Harris book. I reordered them just to make what I think is a little bit more sense out of this stuff. Overview. Access control controls how users interact with systems. Subject, object, and the access is the information passing between these. Most definitions, apart from the text, do distinguish identification and authentication, proving your identity, from what are more commonly called access controls, which is a list of resources that you're allowed to use once you're authenticated. The book, perhaps following after the CISSP Common Body of Knowledge, combines these two into one general category of access controls. Security principles, the things you need to know about security that we're enforcing here. Once again, confidentiality, only disclosing information to authorized parties. Integrity, the information is accurate, complete, and not modified in an unauthorized manner. And then availability, the ability of authorized users to access services when required. This spells CIA, it's not just for spies anymore. A few more definitions. Identification, the assertion of identity, an individual name, an individual account number, policy number, employee ID number. This could be the assertion of identity by a computer service, by a computer machine, the IP address, the name of the machine. It can also be the assertion of a corporate or business identity or the name of a specific role within the business. For example, the corporate secretary may require identification apart from their identification as a specific individual because of the functions they provide. Authentication is what you need to do to prove the identity. I can assert the identity of anyone or anything I wish, but to get any further, I need to prove that I am in fact that entity. Authorization. Given a proven authenticated identity, what actions is the user allowed to perform? What can you do once the system to which you've authenticated knows who you are? And then there's accountability, which is also very important here. Who did what? What actions did the user perform? Obviously, without an assertion of identification, you can't determine accountability at all, and without authentication, you can't reliably assign accountability, because without good authentication, anybody could assume anyone else's identity. Factors of authentication. You assert your identity, you need something else in addition to that assertion to prove who you are. And these basically boil down to three different things. What you know, which is a password or a PIN, something that you memorize that hopefully no one else knows and no one else can guess. You know it, therefore it authenticates you. What you have, something that you clutch in your possession very tightly and no one else has, can steal from you or borrow from you temporarily. That can be something like, say, a token. And then some fact about you, which is called biometrics, things like your fingerprint. These are the factors of authentication, what you know, what you have, and who you are. Now, biometrics, dealing with something you are, it can include things like scanning the pattern of blood vessels in your retina of your eye, examining your fingerprint, which has been done for over 100 years now, palm scans, your entire hand, signature dynamics, how you write your name, keystroke dynamics, the individual variations in how people use a computer keyboard, voice prints, characteristics of your voice that describe you, and in facial scan, recognizing faces, trying to get computers to do something that human beings do very naturally. Biometrics tends to be more expensive and complex than other authentication technologies. It can use any distinguishable trait, physiological or behavioral, for biometrics. Now, biometric authentication is a matter of matching similarities between the saved metric in some sort of repository and the one presented by the individual desiring the authentication at the time of authentication. There's something that represents your fingerprint, your palm, your signature, saved away in a machine somewhere, hopefully very securely, and then when you try to authenticate again and provide this biometric, it compares the two and sees if they match. Well, the problem is these are analog things in the real world, and you never get a perfect match every time you read them. So what happens is you end up with errors. No match is ever completely perfect. Sometimes there's an amount of mismatch that's enough to result in an erroneous decision. A false reject is called a type 1 error. The person should be allowed in, but isn't because their biometric isn't recognized as matching. And a false accept is a type 2 error, which is when somebody who's not the party authenticating manages to impersonate someone. Passwords are something you know. It's a secret word, characters, and number used to prove identity and grant access. It has an ancient use. It predates computers by century. In ancient Rome, Polybius described a system for distribution of watchwords in the Roman military, and even goes back to some of the civilizations of the Near East. It was used in the earliest multi-user computer systems, where in the early 60s folks would log on to dumb terminals and share the resources of a central computer. It's supported everywhere. Every device, every application, every system at some point has password authentication built into it. It is inherently flawed. People choose bad passwords. Passwords are incorrectly stored. Passwords can be guessed. The cryptography used to keep passwords secret can be cracked or are broken with powerful enough processors, and so forth. Despite being flawed, the fact that they're easy to implement, easy to use and familiar, and the fact that they're just very inexpensive means that they're still supported. Ways to get around the flaws in passwords include the use of one-time passwords, which is something you have that generates a password. These are token devices, a separate password-generating device carried by the user, which replaces a memorized password with a machine-generated password that changes on a frequent basis. Synchronous tokens synchronize the time between the token possessed by the user and a central authentication server governing whether the user gets in or not. The one-time password is a function of time and changes with the passage of time. Usually a new password is generated every minute or so. The user pulls out their device, keys in the number that's on the device or the password that's on the device at the time, enters it, attempts to log into the system, and in a similar synchronized clock compares that with what it should be. And if it matches, lets them in. If it doesn't, it doesn't. Asynchronous passwords are not based on time, but instead change typically with each login attempt. A challenge response device is provided a challenge from the server. When you try to log in, you first get some random set of characters or numbers from a server, which you enter into your challenge response device. The device then performs some calculation to generate the correct response to the challenge. You key the response in as a user, it goes back to the server that generated the challenge, and they say, aha, this is the correct response to my challenge. So those are asynchronous devices. It takes a couple of more manual steps, but they're much simpler to use in a lot of ways. And the crypto card you see here is an example of an asynchronous device. Passphrases. A password is a set of random characters. A passphrase is a set of random words. Random words may be easier to memorize than random characters, but are they really more secure? Just because they have more letters in them, because they're words, doesn't mean that they are harder to guess. They aren't secure if somebody's choosing the name of a popular movie or a song for their passphrase. Note that this cartoon here is not entirely correct about the advantages of passphrases. It intends to exaggerate them. And the bits of entropy actually in that passphrase are incorrect. Smart cards. A smart card is a credit card-sized device that has that little golden thing on it that looks like a squash bug, with multiple arms, and that is actually a set of contacts that communicate with and provide power to and input and output to a processor and memory on the credit card itself. Smart cards include processors that can perform cryptographic operations. Hence, if the card stores a private or secret key, their possession of the card comes under the something you have authentication factor. If a user is required to enter a PIN to unlock or use a card, it becomes two-factor authentication, something you have and something you know. Smart cards are designed to be physically tamper-resistant, to make it hard for somebody to break them apart or manipulate them and find out exactly what the secrets are in a chip under them. Though somebody with a very well-appointed lab may be able to get around that. Attacks against them include things like fault generation, where the attacker submits obviously erroneous, incorrect data to the smart card in an attempt to make it fault or generate some sort of strange output in response. Side channel attacks attempt to measure something that's incidental to the cryptography performed by the card, like power consumption, heat generation, and so forth, to learn something about the nature of the process and the cryptographic key. And then lastly, since the smart cards are actually small computers and are run by software, if there are security flaws in that software, that can be exploited as well. The standard for smart cards is the ISO standard 14443. Smart cards in Europe have replaced American-style magnetic strip debit cards, with a great reduction of card fraud as a result. This system is called in the UK chip and pin. The end.